Okay, hi everybody. Thank you for joining our today webinar organized by the Institute of Physics. I'm Stephan Roche, editor-in-chief of Journal Physics Materials. And in a couple of minutes, we will start because we have people joining. So please be patient for a couple of minutes. Hi again. Good morning, good afternoon, good evening. Thank you for joining this webinar, which will be focused on the quantum materials. So now and the future, hopefully we will have some flavor of very interesting research direction. So it's my pleasure to share this webinar. So I'm Stephan Roche. I'm a researcher at the Catalan Institute of Nanoscience and Nanotechnology. And I am also the editor-in-chief of the Journal of Physics Materials, which is organizing this seminar. And the Institute of Physics IOP is the main organizer. So during this hour, let me see if I can move the slide. Oh, okay, so I will first start with some kind of opening remarks concerning our webinar. And then we will have three speakers, Professor José Valenti from the University of Frankfurt, Professor Luis Foà Torres from the University of Chile, and Professor Louis Taillefer from the University of Sherbrooke. So you have possibility to ask questions. You have a chat box where you can that you can magnify actually, and you can ask questions to the audience and to the speakers. So please do not hesitate to type your question during the presentation. We also have a Q&A session at the end of the presentation of Louis. So here again, we will check your questions and we will try to answer as much as possible. Okay, so sorry, not used to. So as I was just saying that I'm in charge of this fully open access journal, which try to combine, we try to attract research at the forefront of material science and technology. We have an interdisciplinary and multidisciplinary scope. This is a journal that has been launched just 2 years ago and is doing very well. We have a lot of different type of sub-communities who have joined the journal. And so we are now trying to disseminate more about what we are doing. And especially today, we have a focus on quantum materials, but the journal is embracing a much more larger scope of material science and technology. So concerning quantum materials, I'm sure everybody is well aware about this impactful work of Pablo Jarillo Herrero from MIT several years ago. He had the very strange idea to start with stacking graphene monolayer on one on top of the other. And that was very curious because till that point, people have tried to delaminate graphite in order to achieve a single layer, and with all the research related to graphene. But it turns out that Pablo was inspired by the fact that a very curious prediction was made years before, that if you rotate one layer on top of the others at a certain angle, 1.1, and as you see in this animation, in this simulation, you will get the bond structure will become very strange, and the emergence of a very flat bands at zero energy, at low energy. So that was pure theoretical calculation, and Pablo surprisingly discovered a completely unconventional physics, and the first physical exotic phenomena that was revealed was this magic angle superconductivity that was really stable at this specific angle. So there have been a lot of activities till today. This is a kind of exploding field of research where one of the main challenges is to understand what is the origin of this superconductivity. But we can see in this field that there are a lot of issues that actually are common to many other materials, and that's why we encourage you to consult this broader overview about what are quantum materials today. This is one of very recent roadmap that we have elaborated with a panel of experts, and we are not just looking at twist layered materials, but we are trying to give a picture about the current stage of progress and the challenges and the perspective concerning a series of quantum materials, where in a lot of them you will find a topological properties or quantum entanglements and many open questions. So that's very stimulating, and also very stimulating to have all these sections packed together, because when you read them all, you find easily that there are some common issues and common questions. So I hope that during this session, where we have picked up 3 sections of the roadmap, Jose will present quantum spin liquid. Luis will discuss non-equilibrium phenomena in quantum materials, and then Louis will discuss cuprate superconductors. Okay, so beyond this roadmap, in the Journal of Physics Materials, we have also several other possibilities to contribute if you're interested. First of all, I like to encourage you to consult this topical review, because it is it is the most impactful paper actually of our journal today, and this is because it shows the very important, the large concern, the very useful use of machine learning in order to investigate complex materials. So that's something that is an emerging field, I would say, and definitely in this review you will find a lot of indication, a lot of knowledge about where this type of methods are actually employed to accelerate the study of these materials at large, not just topological materials, but all kind of materials. Even many body physics can also benefit from using machine learning based algorithm. Okay, so I have just a kind of self-promotion of one of paper where I published in the journal with some colleague, and in which we illustrate the use of machine learning for designing a very accurate interatomic potential in different type of exotic two-dimensional materials. And thanks to that, we can compare with DFT once the machine learning training potential are found, then they can be used in very large scale materials, and for instance we can investigate their thermal properties. So this is one example of my own contribution to this journal. Okay, so that's said, I like to promote also a very recent open focus issue that we have launched. Luis is one of the guest editor, and in which you are welcome if you want to contribute to submit your paper, and there will be let's say a focus on strongly correlated system and out of equilibrium physics, with concern on topological material, 2D twist materials, magnetic skyrmions, but I think the guest editor will be happy to enlarge the scope. So if you have some paper, a very nice paper, you are able to submit, but you still doubt where to submit it, I strongly encourage you to try our journal. You will see that we will do a lot of promotion of your papers. Okay, so now I would like to introduce our three speakers. I'm very happy to have them here. We really appreciate that they will make this presentation. José Valenti from Frankfurt, Luis Foà Torres from Chile, and Louis Taillefer from Sherbrooke. So we will start with José, who will discuss quantum spin liquids, challenges and opportunity. So when we are switched to José, then José can start. Very good.
Okay, so you see my talk?
Yes.
Yes. So thank you very much, Stephan. It's a pleasure to be here. And today, indeed, I would like to talk about quantum spin liquids. This has been one aspect that has been touched upon in this quantum materials roadmap that was led by Stephan, and there were many of us contributing, and it was a pleasure to contribute. And today I would like to talk a little bit about designing quantum spin liquids. What are these type of phases? Where are the challenges? Where are the opportunities? And also what kind of technological use one can have out of these very exotic states. So of course, first of all, I would like to start by defining what do we understand as a quantum material. Stephan has already shown some examples of quantum materials, but let me give you my definition, because this is in fact how I'm going then to work out this concept of quantum spin liquid. So quantum materials are, for instance, a piece of iron is a quantum material if we interpret it in terms of the constituents, of the microscopic constituents of this material, which is formed by atoms, iron atoms, which are forming a lattice. And these atoms have, of course, the nucleus and the electrons. And what is, in fact, in solid state physics, what is important is the role of these electrons that are interacting among each other. And if we consider a cubic centimeter of such a material, we have 10 to the 23 interacting electrons. And of course, the electrons have intrinsic properties, which is the quantum nature of these entities, which is they have a charge, they have a spin, they occupy orbitals, and of course they interact with this lattice. So basically where the atoms are ordered. And it is the simultaneous action of all these degrees of freedom that gives rise to distinct phases of matter. So the concept of emergence that comes out of many constituents collectively interacting among each other. And this concept of emergence, in fact, goes back to Phil Anderson. So here I'm quoting his work, More is Different, which is in fact the beauty of all these quantum materials, that you can get new type of phases from basically this collective effect of the constituents. This concept of emergence, we also have it classically. In fact, we have some analogies there. If we think about a flock of birds, we think about the birds individually, we will never ever predict that they could build these very nice, in fact, these very nice images when they fly together. So that's in fact an emergent state that comes out of basically this collective effect between the birds. However, in the case of quantum materials, we have the nature of the particles is a quantum nature, and we are going to see these macroscopic manifestations of this quantum nature, like superconductivity, magnetism, and many other properties that we will see, in fact, today in also the talks to come. So now what I want to concentrate on is, for instance, magnetism. So I'm going to indeed take advantage of the fact that the electrons have a spin, and therefore they can, by the interaction among them, they can build states like ferromagnet or antiferromagnet when they have long-range order. However, we want to have states that are beyond what is already known for decades, this magnetism, what we call the traditional magnetism or paramagnetism, if we have that we go to high temperatures. So how can we make states that go beyond these ordered states that are known for centuries? And one of the way of getting new type of states is by promoting quantum fluctuations. In fact, this has been looked for since many, many years. Phil Anderson was one of the first thinking about how to get new states by promoting quantum fluctuations. And he was introducing this concept of quantum spin liquid that I'm talking about today. So how can we promote these quantum fluctuations in these magnetic systems? So one way is by considering what we call geometric frustration. So if we have these spins of the electrons in a lattice, like a triangular lattice or a Kagome lattice, where, as you see here in this middle panel, where I have, let's assume that my spins, which I consider now having one spin in each of these lattice sites, I assume that they interact antiferromagnetically, so they are anti-parallel. You see already that the third spin, there is no way to align itself anti-parallel to the other two. So this spin is in what we call a magnetic frustrated state. So what does the system do in order to get rid of this frustration? And this is when we have indeed quantum mechanics at its best. So what happens then is that we have a linear superposition of the up and down at the same time. We can describe it in this way. So if you know, of course, you know very well about the Schrödinger cat dichotomy. So having a superposition of a cat which is alive or dead, of course, in a macroscopic wall, this is not possible because of incoherence, but in the microscopic wall, we can have this manifestation of having this linear combination of two states, in fact, because we have this possibility of coherence. So this is the type of states that you can realize, which is a state that the representation that I have here is only to represent these linear combinations of up and down spins, but it has very interesting properties, such a state, which are, for instance, that they have topological long-range order, and the topological invariant, for instance, can be defined as the number of even or odd valence bond. We call this linear combination of up and down and up between neighbors. So having these even or odd number bonds crossing, in fact, one row. But this topological long-range order is very different from the long-range order that we know from a ferromagnet or an antiferromagnet. So this is a cooperative quantum phase with fluctuating spins down to very lowest temperatures, and there is no symmetry breaking. The ground state is long-range entangled. And now what is interesting, and this is why these type of phases are interesting for, in fact, technological possibilities of application, is because the excitations at these states are fractionalized excitations. What do I mean by that? So fractionalized excitations are excitations that are neither bosons nor fermions. So for instance, here I have the representation of a spin. So let's assume that I give energy to my spin liquid. This energy breaks a bond, breaks one of these valence bonds. And what I have now is this spin that it is unpaired. But due to this environment with the surrounding, what I do have is a particle that has spin but has no charge. And this particle, in fact, is what we are calling a collective excitation or quasi-particle, which has very special properties because of this fractionalization, because it is neither fermion nor a boson. There are many of these quasi-particles that you can, in fact, create out of these spin liquid ground states, like Majorana type of excitations, which are described in terms of Majorana fermions. These are again particles that where the particle is the same as the antiparticle, so they have no charge and spin 1/2. And here is where I want to go into the direction of quantum computing, since Alexei Kitaev, in fact, what he showed is that if you take a very frustrated system like the ones I was showing to you, so in this case, this the type of Hamiltonian that I'm showing, or the system that I'm showing here, this is a highly frustrated system because what I'm having is an Ising model, a Nias-Neighbor Ising model, where the interaction between the Nias-Neighbor is depending on the bond where I am in this honeycomb lattice. So now if you think that you are this side here, you are interacting with your neighbors with a different component of the spin. And because in quantum mechanics, these three components don't commute, you have a strongly frustrated situation for this type of model. And what is interesting about this model is that it can be solved exactly. The ground state is in the quantum spin liquid because this is the type of state that you realize when you have this strong magnetic frustration. And the excitations are these fractionalized excitations that I was telling to you, these Majorana fermions. Mathematically, you can show how you can go into this exact solution of this Hamiltonian. So now the point is that with this type of fractionalized excitations, Alexei Kitaev did a proposal of building topological qubits based on these anyons, so that when you are now considering the properties of these anyons, when they are, in fact, they are non-abelian particles, you can make operations between these qubits that are protected by topology. So one of the big issues in topological, in fact, in quantum computing is the fact that you have problems with the coherence when you do operations. Now, working with this type of materials that have these states and these excitations, then you would be able to have these operations in your quantum computer that are protected by topology. So this is one of the directions that one is going to, in order to have indeed some platforms for quantum computing. But now the question is, because we are talking about quantum materials, where do we find these quantum states in nature? I have described to you the state, but now I want to find where to go to look for in order to have the realization of them. So this is indeed the big challenge, to go to have this connection between materials that then you can indeed functionalize by making use of these properties, and the prediction of this type of states, this quantum spin liquid. So these are our challenges. And since I am a theorist, so the challenge for us is indeed to do the prediction. So to do the prediction, it means that if we want to do this prediction from first principles, so by taking into account the basic interactions between the components of between the electrons and the lattice, we need to solve the Schrödinger equation. And there is a lot of, in fact, there has been a lot of development in methods, analytical and numerical methods, trying to solve these equations, especially for this type of systems, starting from density functional theory, using machine learning, in fact, algorithms, many-body type of methods. So since my time is not very long, let me go now, in fact, to the slide that, in some sense, brings together how we do these predictions, since it is very important when one tries to find in nature materials that have this type of, in fact, states, that there is a very strong collaboration between the theoretical predictions, where you have to do numerics, or mostly numerics, because of solving these equations, you have to go to the computer. But when you are trying to really think about materials, it's very important to have a strong connection with the solid state chemists and physicists that do the synthesis of these materials. So there is a back and forth guided growth between the theories that do predictions and in fact the synthesis of this type of materials. Moreover, these materials need to be in fact analyzed. So that means that we need also very strong collaboration with the experimentalists that do measurements on these materials to really test and prove that they show these properties that we would like to have. And of course, there is then a feedback going back to theory and the computational work, which is motivated by what is being observed by experiment. So very often we hoped to have a certain property, but by doing all this process, it turns out that a new different property comes out of it. So therefore, this is the challenge that we are at in this century, indeed, to have very strong collaboration between theories and experimentalists and synthesis colleagues, in order to be able to predict and to be able to realize these very exotic phases of matter and functionalize them in the long term, these materials. And this has been one aspect that we treated in this quantum materials roadmap. And I'm open now to your questions. I think my time is over. And therefore, I give back my...
Okay. Thank you very much, Rosa. It was great. It was really great. I have plenty of questions myself, but I would start by one question. Are quantum computers, there are already operational quantum computers in the market, and one of their use is to try to help solving complicated models. So I'm wondering, in quantum spin liquids, if you are using quantum computer, or this is something that is becoming timely, and what are the possibility of existing quantum computers to solve some of the questions that you like to answer?
This is a long throw, indeed, because there is, I would say, 3 steps. One is first to realize the quantum computer, and what I was showing to you, these topological qubits. Right now, the big challenge is to build these topological qubits. So, for instance, Microsoft is working on that, and many other groups. So this is one part, to build the computer. But then what you are asking is, once we have this computer, and in fact, all the type of platforms are more advanced than these topological qubits, how can we use them in order to make our computations, right? This is, I think, your question. Now, for that, we need to adapt our software, because when you work on a quantum computer, your algorithms have to be adapted in order to make use of the quantum computer. And there are many groups, in fact, working on that, trying to adapt the algorithms in order to make them useful also for this type of calculations. And I really think that for some questions, this will be extremely useful, because we will have other means of indeed dealing with the complications that we have right now in the classical bit world.
Okay. Oh, well, great. So I have more questions, but I will, if you're okay, we will move to the next speaker, and we keep this question and others. I hope will come in the chat for the Q&A session. Okay. Thank you again, Jose.
Thank you.
So now we switch to Luis from University of Chile. So Luis will give us a flavor about how non-equilibrium phenomena are becoming more and more important in quantum materials. Thank you, Luis.
Thanks a lot, Stephan. Hello to everybody. I'm happy to be here today talking about this brief perspective on quantum materials from the viewpoint of non-equilibrium. So I'm Luis Foà Torres. I work at the University of Chile. This is located in Santiago, in just the center of the country, right here. I'm actually from the other side, from Argentina, but I have been working here since 2016. Santiago is quite a nice city. We have very tall, very high mountains very close. We have Aconcagua that is almost 7,000 meters, very close. But from the city, we can see actually peaks of up to 5,500 meters. And it's quite interesting landscape, as you can see here. So today I'm going to talk about non-equilibrium phenomena in quantum materials and give you a brief perspective. You can enjoy section, for example, if you're interested in this topic, section 11 of the quantum materials roadmap that that Stephan and Jose mentioned before. This section is something we wrote together with James McIver, and it's especially devoted to this area. And so there you will find many challenges and a brief overview of the field and many references. So I hope that you enjoyed. So this field of non-equilibrium phenomena in quantum materials has by now has several decades. But I think I'm right if I say that the last years have been particularly exciting, and we can feel some sense of an accelerating pace in this field. And so I will mention some of the things that contribute, that converge into this field. One of them, probably the one that has more time in development, has to do with ultra fast photo-induced processes. You use a very fast and strong pulse, and for example, take material from an equilibrium state to a very, very excited state, non-equilibrium state, and then from there the system may decay, for example, to another metastable state that would not be possible to reach otherwise. Or in some other cases, you may do this excitation, then the system keeps oscillating around metastable minima, and then you are essentially triggering order parameter oscillations. And this has been helped a lot by technology and development in instruments over the last years. So this is one of the sources, but you can also explore what happens during laser illumination. This is something that started to be done more frequently during the last years, and then you can actually try to use light actively to make changes and try to see what happens while illumination is there. And I find this very exciting. This contrasts a lot with what you do, for example, with light. Usually, that you try, for example, if you take Raman spectroscopy, it's a wonderful tool for 2D materials and many others, especially with graphene. And so, but there you're trying to use light in such a way as to observe the properties of the material that are there, and you don't want to change them. But you can actually use light to change these properties, and this opens a whole new place for research. So I will mention a couple of other lines that contribute to all this field of non-equilibrium phenomena coming more from this side. So during the laser excitation, you can actually change the properties, and a very wonderful experiment during doing this is some series of experiments by people at Nugedic's lab at MIT. What they do is they use a special ARPES technique where they have a laser that actually modifies the properties of the system, and then you can see what happens to the band structure. And for example, here in this very nice image from Basov's review, you can see that actually during the peak of the pulse, you can see that the band structure changes a lot. This corresponds to what happens at the surface of a three-dimensional topological insulator, was originally reported in this paper back in 2013. So at the surface of a 3D topological insulator, you have something that is very much like graphene, but now with a stronger curvature. So you have a cone, and during this pulse, during the peak of this pulse, what you can see is actually that instead of having a single cone, you start having like the cone with a lot of replicas here. And these replicas react a lot to laser polarization. Depending on the polarization, you can even gap them. And so this is essentially a manifestation of hybrid electron photon states of matter, the so-called Floquet-Bloch states. And so this is essentially manifestation of this, and you can actually tune this with a laser that you are applying to the system. And so this is a quite exciting line that opened the door for new experiments that I will mention later. And somehow conceptually related area, but dealing with different systems, is to try to use driving to engineer effective Hamiltonians. So there, essentially, you have a system that most of the time it's could be ultra cold matter, could be other sort of systems, and then you apply driving, and you try to use this driving to engineer an effective Hamiltonian. A very nice example in this area is these experiments done in Zurich, where they use driving on ultra cold fermions to realize the Haldane model, something that that looked very, very difficult to achieve in normal material. They managed to do it there thanks to using this driving. And so these are somehow a couple of nice examples. What I will do now is try to somehow get through this rabbit hole around this area and show you some of the things that are on the other side. So on the other side, you will see a lot of people looking for actually making quantum phases on demand by using an external source. I like to think of this as one of the pursuits is to try to use light as a topological switch. So essentially, you have a material that doesn't have topological states, like for example, graphene. Now you turn on a strong laser illumination, and you use this interaction, light matter interaction, to actually introduce states that are new, that are hybrid electron photon states, and you are able to change very, very delicate properties like the existence of a gap, the presence of edge states, and and this is what people many times call Floquet topological insulators. And this is one of the things that many people have been doing. These are two of the funding references in this area. And immediately, if you think, like for example, you use graphene and you shine a light of a specific frequency strong enough, and you change its properties and develop topological states, as it was predicted originally in this paper by Oka and Naoki. Immediately, you would think, is there a Hall response associated to these states? And this is something that many people have been studying for a couple of years, including some of our own papers, predicting Hall response in these systems that are illuminated. And this, for example, has been realized in these experiments that were reported in 2020, last year. It's people in Hamburg, James McIver, Andrea Cavalieri, and others. They reported the realization of this light-induced Hall effect in graphene. And for example, in this figure, you can see the Hall conductance as a function of Fermi energy for different intensities of the radiation. You can see that as the intensity increases, you develop a sort of plateau that gets close to 2e squared over h. That is exactly what the predictions say. And so this is, I find it quite exciting, and you can check what happens for different energies and stuff. This is using light in the mid-infrared range. That is very important for this to happen. And so this appeared only last year, and it's I think that many new experiments in this area are needed, especially transport experiments, so to be able to have a better grasp of what's going on here. There's of course a lot of also dissipative effects that will be important. So this is very similar to a quantum Hall effect, but with many important differences. As this is a non-equilibrium situation, as I said, there will be dissipation. There are many differences with the correspondence of these plateaus with the number of channels, that a topic on which we work before, and it's quite exciting as an area. There are many more things that I expect to come next, and I like to think that that a way to do inference in the future is to look a bit at elements that we have in the present. So as someone said, the future is here, it's just unevenly distributed. So if we can take some elements of what's going on today, we can have an idea of what could be going on later. And so I will comment a bit on this. For example, there are some very recent experiments where new topological phases with no counterpart in static systems have been realized. The realization of this anomalous Floquet topological system in ultra-cold atoms is something that was reported last year based on some predictions that were made earlier by other people. And there's also the possibility of doing laser-assisted control of phases that might seem impossible to break with such a small perturbation as just putting a bit of light. And one case is the quantum Hall effect, that is perhaps the most robust topological phase you can have. While shining strong laser illumination with specifically tuned frequency can change a lot the quantum Hall plateaus, and actually you can even reverse the sign of the Hall conductance depending on your laser polarization, something that we studied this year and appeared in a recent paper. You can also try to use light to somehow achieve new properties in quantum spin Hall states. So if you shine light on a 2D topological insulator, you can generate the spin polarized tunable photocurrents. That is something that we also studied recently, and that I hope that may foster new experiments. But there's much more. You can also revisit many things that have been there for years and are still not quite well understood, as the problem of shift photocurrents. And under this new sort of framework, you can try to revisit this and get a better understanding. Also, other work we did in the past and that we published in Journal of Physics Materials. And what I think it's even more interesting, it's to think about what people started to call self-Floquet systems. So it's essentially to bring emergent phenomena to these Floquet systems I was mentioning. So these systems that are where light-matter interaction is strong. And the very nice example is this paper that appeared in 2019 in Nature Physics, where what they do is they think of the problem of shining linearly polarized light on graphene, and tuning the frequency in such a way that you tap onto a plasmon resonance in the system. And if you do it properly, although linearly polarized light has no chirality, once you exceed a given threshold for this driving amplitude, the system spontaneously generates a chiral motion for the electrons. And so with this chiral motion, you generate very phase effectively, and magnetization that is purely orbital in this case. So spin is not involved in this. This is one of the ways in which I think we will expect, one of the directions in which we will expect many more works in the future. There's many very interesting works on light-induced, for example, charge density waves in materials, where start to get more complicated and even more interesting, perhaps. So overall, I would say that we have really many possible directions. I would point as emergent out of equilibrium phenomena as really something that will become more and more common in new research. Essentially, what we will be looking is at what happens when given some external energy sources. I said the laser most of the time, but you can think of other sources of energy. And once these sources exceed a given threshold, you can get emergent phenomena that can become more interesting and perhaps more useful. People are thinking in several directions, like more lacing-like phenomena in quantum materials. You can also think of using cavities of strong laser pulses and having better control, and I think that this is going to become more interesting and more common in the coming years. And there's a lot on photo-induced superconductivity and states, temperatures that could be enhanced, or perhaps new states that could be made. There's a lot on non-emission systems that I hope that this could merge. What we have, time crystals, new metal phases. There's a very nice, for those interested in photo-induced superconductivity, there's a very nice review by Andrea Cavalieri that is there, and this will help for the next session somehow by Louis. And there's also a review I wrote for Journal of Physics Materials on non-emission systems that you may enjoy. And so, just a final word, I think there are a lot of promises in quantum materials beyond equilibrium. For me, going beyond equilibrium is really a creative resource for breaking the rules, for being able to achieve things that would not otherwise be possible. So thank you for your attention.
Thank you so much, Luis. Okay, I think that your conclusion, there are many rooms at the bottom, huh? Like
Yes.
like our famous friends were saying a lot. So yeah, that's really fascinating. I have many questions too, of course, but I have just one, because all that you have shown, of course, there are many perspectives, but there is also an interest in trying to make vibration topological, no? Topological phononics,
Yes.
also topological photonics. So I'm wondering if you have envisioned, or if this is something that has been already investigated, the possibility, probably in electrical insulator, to excite, to control vibration modes and make them topological by absorbing light. Is it something completely crazy, or that could?
No, I think this is at the heart of many. It's very good question, Stephan. It's at the heart of many things that we could see in the future, because actually there are some reports on people trying to get to topological phases with phonons, but and we also have a couple of works on this one that appeared in the archive 2 days ago on the interaction between electrons and chiral phonons in 2D materials. And so we see that we can achieve states that are quite robust. They are co-propagating, but they coexist with bulk states. In that case, it's not, we are not sure that there's a topology behind, but they coexist with the bulk states. So at the end, you have a metal that is a bit weird, because you have a metallic state where you have some states, a subset that is strongly correlated with the phonons. And then to achieve this sort of states, what could be crucial is to use you need an external energy source. This could be, for example, light, strong light. You can use this external energy source to pump energy into the phonons and eventually select these phonons for them to make more interesting things and to have some emergent order. So I would expect that if you exceed a given threshold, new things could happen.
Okay, great. That's super. That's super. So there are some questions. I cannot read them in my chat. Maybe my colleague from IOP could. I don't know if there are so many questions, and we have to retain them for the Q&A session. But yeah, I cannot really check my mail to see this question. So I don't know. Maybe Alex or Ansel, if you like to bring one more question for the moment to Luis at that point, or we just keep for the Q&A as you think more appropriate, or maybe we will. Okay, let's try. You will send me this question by email. I would check, and maybe I think it's better than we move to Louis. Thank you, Luis. Okay. So please stay a little while for the presentation of sure. Louis and the Q&A. So now we move to Louis Taillefer. And so I will ask my colleague. Okay, we're already on his presentation. Thank you, Louis, and sorry for the problem with your webcam. So I hope that we can solve this next time. But now it was a bit complicated. Thank you, Louis, for your talk. So we need maybe.
Thank you very much, Stephan. So can you hear me?
Yes, we do.
Yes. Okay. Yes. So apologies for the not having a webcam to be present visually. So my talk today will be on cuprates, fascinating class of quantum materials. I'm based at the Institut Quantique in Sherbrooke, Canada, and I'm also part of a program called the Quantum Materials Program at CIFAR, Canadian Institute for Advanced Research. So the superconductors are fascinating type of quantum materials. You know, superconductivity is this amazing state whereby electrons enter a new phase below a critical temperature Tc, where they pair up and are able to conduct electricity perfectly. So many applications follow from that property. Now, this superconductivity was discovered more than a century ago, but more recently, various families of what we might call new superconductors have been discovered. And here I illustrate 4 of them: organic superconductors, iron-based or pnictide superconductors, heavy fermions, and then cuprates. And just I'm showing this just to show phase diagrams, typical phase diagrams for the different families. And what you see, for example, in the first 2 is that there's a phase of magnetism or spin density wave that can be suppressed by tuning some parameter like pressure or concentration. And when you do that, superconductivity appears. Now, in these first three families, where the magnetism is a metallic phase, it's believed that superconductivity actually comes from, or the pairing comes from, spin fluctuations associated with these antiferromagnetic phases, as opposed to a phononic mechanism in more conventional superconductors. Now, in the cuprates, the situation is more subtle. And so cuprates will be the focus of the talk today. So here's the phase diagram again. So temperature on the y-axis is a function of doping. Doping is basically electron concentration. So we go from 1 electron at 0 doping here on the left, and we decrease the electronic density as we increase doping P towards the right. And so the interesting thing about cuprates is that actually they start off as insulators at 0 doping, and they become metals as we increase the doping. And they're good metals on the right here. In between, we have this superconducting dome bounded by Tc. But there are other phases, like a charge density wave phase, which we won't discuss today. But there's this still mysterious phase called the pseudo-gap phase. You might call it the dark phase of quantum matter. It's bounded by a temperature T star and a critical point or doping P star. And so in this talk, I'll show you that even though these materials have been discovered now 35 years ago in 1986, there's still a lot of new phenomena being discovered. And I'll focus on 3 such phenomena that I called strange metal. So this is the fact that the resistivity, if you sit just above the critical point here, P star, resistivity is perfectly linear in temperature as you go towards T equals 0. And that's in contrast, of course, to a conventional metal where the resistivity would be a T squared. We will look at what happens when you cross P star, and the signatures look very much like what we call a quantum critical point. So we'll look at that. In particular, the carrier density undergoes a dramatic change. And finally, a more recent property that has been discovered is that phonons carry a thermal Hall effect. So we say that the phonons are chiral, by which we mean that they have a handedness in the presence of a magnetic field. And I'll end with that particular property. So let's start with a strange metal. This is the fact that, here's a cuprate phase diagram again. If you go to the end of the pseudogap phase, and these are various experimental signatures of that phase. If you go to position yourself just beyond that phase, and you measure the resistivity, as a function of temperature, you find that it's perfectly linear. And these measurements are done, as most measurements all show, in the presence of large magnetic fields to actually suppress superconductivity and be able to go down to low temperature. So this is for one material, bismuth 2201, and then a completely different material, but also just above its critical point. You have again a perfectly linear temperature dependence. So this is a rather universal phenomenon in cuprates, this T linear resistivity. And it's very puzzling from a theoretical point of view. How does it come about? Now, one of the new findings about T linear resistivity, and this was pointed out by Andy McKenzie and colleagues for heavy fermions, for example, an organic superconductor, is that if you estimate the slope, if you take the slope of the resistivity, the T linear resistivity, so this coefficient A1, you can show by using a simple Drude formula, knowing the carrier density and the mass, that it comes from a scattering rate, which we say is Planckian. We have a Planckian scattering rate or Planckian scattering time because tau is basically equal to h bar divided by kBt. So this factor alpha here is of order 1. And so there's the qualitative aspect of perfect T linear resistivity, and there's also the quantitative aspect that in many materials, and this is for cuprates now, for all sorts of different cuprates, including electron cuprates, you find that alpha is of order 1. So how does that come about? And if you want to read more about this, there's a nice article in Quanta by Natalie Wolchover that was published in November 2018, which you can read. I might point out, as mentioned by Stephan in his introduction, these twisted bilayer graphene has a lot of interesting properties, superconductivity being one, but also this Planckian dissipation is observed here as well. So there's interesting connections to other types of materials. So in the cuprates, one of the questions is how does one go from T linear resistivity, which is in red here, to this T squared Fermi liquid resistivity at high dope? So going from T linear to T squared. And so recently, working with Brad Ramshaw at Cornell, my postdoc Gaël Grissonange, who is now a postdoc with Brad, has looked at this question from using a different measurement, which is called ADMR, so angle-dependent magnetoresistance. The beauty of this measurement, which is simply to measure C-axis resistance of a 2D material, quasi-2D material, and change the angle of the field, is that the change in the resistivity that you measure, and there's an example taken from a paper by Nigel Hussey on a strongly overdoped cuprate, is that you see various wiggles, and as a function of the two angles. And these wiggles basically derive from the shape of the Fermi surface, so its corrugation, for example, and the angle dependence of the scattering rate. So you can do calculations that reproduce the data and allow you to extract this information. This measurement is done typically in very high fields. So our measurements were done in the highest fields available in the world at the moment, steady field at the Magnet Lab in Tallahassee. So specifically, we looked at this particular cuprate NDLSCO just above the critical point, and then we can compare with earlier data well above the critical point in this system here. So this is the data this is what the data looks like. So this is resistance, C-axis resistance as a function of angle. You can see that for different azimuthal angle, you see different features, and you can reproduce these experimental features essentially perfectly by fitting a tight binding model. That then gives you back the exactly the Fermi surface that you would measure by RPES, for example. So the Fermi surface is confirmed, and then the extra information you get is the scattering rate. So one finds that to account for the data, you require to have a scattering rate that consists of two parts: an isotropic part, this is a polar angle, an azimuthal plot, sorry, of the scattering rate. So an isotropic scattering rate plus a strongly anisotropic one. And what we found by doing a study as a function of temperature is that the anisotropic scattering rate is independent of temperature, so it's elastic scattering. However, the isotropic scattering varies linearly with temperature, and moreover, its slope, so the slope of the scattering rate, 1 over tau, is Planckian in the sense that this parameter alpha is of order 1. So the discovery here is that what gives rise to T-linear resistivity is an underlying scattering rate that has a Planckian magnitude, but moreover, which is isotropic. So then we can compare our data very close to the critical point to earlier data by Nigel Hussey further away, where the resistivity consists of a small T-linear resistivity plus a T squared. So we're not quite fully T squared yet. That would happen out here. But on the way to getting there, what we find as a function of angle is that the scattering rate, when the system has pure T-linear resistivity, is independent of angle. So it's isotropic. Whereas when you go away, you acquire strong anisotropy. So we see that with these ADMR measurements, very recent ADMR measurements, we can shed further light on this intriguing physics of Planckian dissipation. The second topic I wanted to mention here is what happens at this quantum critical point, or this critical point that you tune as a function of some parameter x. In our case, it's concentration, but it could be pressure. In the usual case, for example, organics, pnictides, heavy fermions, you have a well-defined long-range magnetic order, which you know ends at this critical point. And then you have phenomena like T-linear resistivity out here and superconductivity around the critical point and so on. And of course, as you cross from the right to the left, your metal will change its properties. In fact, what happens is that the magnetic order reconstructs the Fermi surface. So you can detect that in various ways. This is one of the ways this was done in cuprates recently is by looking at the Hall number. Okay, so these are measurements performed with Cyril Post in Toulouse in the high field lab, pulse field lab, up to 80 Tesla. So what is plotted here is the Hall coefficient of a cuprate. In this case, it's YBCO. And as you increase the field, you're able to suppress superconductivity, which you see down here with a 0 signal. And the value that is reached at high fields in the normal state depends very strongly on the doping. So now what we can do is plot not RH, but 1 over RH, or the Hall number that you can relate to a carrier density. So this is what's done over here. So this is the Hall number per copper. And what you find is that basically what happens as a function of doping when you go from the Fermi liquid on the right to the mod insulator on the left is that the carrier density goes from 1 plus P, drops rapidly to P, and then stays P. Okay, so 1 plus P to P is a new signature reproduced in other cuprates since then of this critical doping associated with the pseudo-gap phase. And so this actually is very much what you expect for antiferromagnetic order that would introduce a change in the Brillouin zone that reconstructs the Fermis. Now, and theoretically, this in blue reproduces very well. So this is the puzzle. puzzle is that it looks as though the pseudogap phase is antiferromagnetic order, but in fact, when you look at, for example, recent data by Marc-Henri Julien and David Leboeuf, they only see some kind of spin glassy magnetism at very, very low temperature, much lower than the pseudogap temperature. So at the moment, the pseudogap phase looks more like a phase of short-range antiferromagnetic correlations, but yet with signatures that look very much as though there is long range. So that's a continuing area of research. Let me come to the last topic I want to mention, which I call chiral phonons. Now the Hall, here the measurement is a thermal Hall effect. So you send a heat current along X, a field along Z, and you measure the transverse temperature difference, delta Ty. And that gives you kappa XY, the thermal Hall conductivity. If you perform this measurement well above, well, just above the critical point, so outside the superconducting, the pseudogap phase, in the presence of a field where that suppresses superconductivity, here's what you see. The red data is kappa XY over T versus temperature, okay? And the blue data is the electrical Hall conductivity, sigma XY. And you can see that the two become equal at low temperature modulo this universal constant. And that's just the Wiedemann-Franz law. So that shows you that basically everything is normal. The thermal Hall is equal to electrical Hall, as you would expect in a metal. The puzzle came when you reduce the doping inside the pseudogap phase. Now the thermal Hall conductivity actually becomes negative, while the electrical Hall remains positive. So there's a new negative signal that appears as you go inside the pseudogap phase. And in fact, even if you decrease the doping down to 0, you continue to see this negative thermal Hall, now in an insulator. So we know that this negative signal is not due to electrons. We can show, and I can discuss if you like in the question, that it's not due to magnons either. So in fact, what we're able to show is that it's due to phonons. So phonons that respond to the field as though they were chiral. And so that's why we call them chiral phonons. And the way we showed this is by actually sending heat, not in the plane of these two-dimensional cuprates, but perpendicular to the plane. And the only thing that actually carries as mobility perpendicular to the planes are the phonons. And we see an isotropic response, and that's what led us to the conclusion that phonons are responsible. Now, just to finish, this is turning out to be a wide open question. What makes phonons become chiral in material? And insulators in particular. And here I'm showing an example of spin liquid, the kind of materials that Rosé discussed at the beginning. And this is ruthenium trichloride, an insulator with the so-called Taillefer spin liquid, attracts a lot of attention, and it has a finite thermal Hall signal. And the question at the moment is whether this signal is due to magnetic excitations, like perhaps Majorana fermions, or in fact, phonons that couple to the magnetism. So this is a broad field now. And let me end then by summarizing the perspective on new directions in cuprates. I've talked about 3: strange metals, quantum critical behavior, and chiral phonons. And I've shown that, in fact, all 3 link the cuprates to other materials. I've mentioned the example of twisted bilayer graphene for Planckian dissipation. Of course, a quantum critical point is something that's seen in peptides and heavy fermions and organics. And now spin liquids are being compared to cuprates in the context of understanding why phonons become chiral. So thank you very much for your attention.
Thank you very much, Louis. Thank you very much. So it was really fascinating. And so I will take, Louis, a question that we have from the chat, the participant, which is directly addressed to you. So the question is, cuprates are known to be ceramic-like, thus the measurements of the anisotropic scattering rates might be affected. All the samples are prepared in your measurements.
So these, I should stress that these are single crystals. So they are ceramic in the sense that are oxides, but they are actually single crystalline materials with very well-defined directions. So there's no ambiguity about the direction of the current in the direction of the magnetic field. So we can actually plot out the angle dependence of the scattering rate extracted from this ADMR technique as a function of direction in the plane. So it's a K-resolved, momentum space resolved scattering rate. Yeah.
Okay. Okay. I have a question myself. When you were mentioning this Planckian regime, where you have the we call a connection between the inelastic scattering time and the Planck constant and KBT. But in elastic scattering time, it's in my mind, it could be due to electron-electron scattering or electron-phonon scattering. And both mechanisms are usually, they will give a very different behavior of the resistivity. So in what you have shown here, is it a kind of universality of this regime, regardless of the temperature and the contribution on one scattering mechanism with respect to another?
Right. So I should have emphasized this more. This is a very good question, because one can observe T-linear resistivity at high temperature from phonon scattering. In fact, it's been known for a long time that you get T-linear resistivity. More recently, people have argued that there's a Planckian limit for phonons scattering electrons. But in our work, and what I've shown you here, we were really looking at the resistivity in the limit of T equals 0. So this is the limit where it's not phonons that are scattering the electrons. It has to be the electrons. So for sure, in our work and the work of others in the low temperature regime, it's really the inelastic electron-electron scattering rate that is at play.
Okay. So whose interpretation is still debated?
Well, there's no theory that actually produces a perfect T-linear resistivity with that kind of magnitude. So it is a beautiful theoretical problem to explain, in fact. And it's universal in the sense that, as far as we can tell, any material, and this now includes, twisted bilayer graphene and organics, any material that shows a T-linear resistivity, if you estimate its scattering rate, it will be of the Planckian value.
Wow, wow. That's really fascinating. I also, because I read again your section in the roadmap of quantum materials, and there was plenty of open questions, and you say that actually probably cuprates are the most enigmatic quantum materials. So one of the points you discussed and was the originating of the pseudo gap, and I think today you connect this to the possibility that this would be explained by short-range antiferromagnetic correlation. So is it something that is settled down, or still there are some different alternatives to explain that?
Well, there's been a lot of progress theoretically, and in fact numerically, I would say, by people like André-Marie Tremblay, my colleague here at Sherbrooke, or Antoine Georges at the Collège de France and Flatiron Institute, and many others. They really have made progress in actually solving the Hubbard model as the prime model for cuprates, and they do obtain a pseudo gap phase. That phase is metallic. It does not have long range order. And if you try to describe, and it has a pseudo gap, if you try to describe it in words, these people would tell you that short range antiferromagnetic correlations is probably the way you could summarize it. Of course, these are numerical calculations, but a lot of the properties are actually in agreement with experimental observation.
Okay.
So yeah, theoretical progress is significant in the recent years, and it's pointing in that direction.
Okay, wow, fantastic. So we will take like probably 10 more minutes max to bring additional question that we have in the chat. Also, I have a few more questions to Jose and Luis. Jose, it was great that you point out the fact that when you have frustration, this stimulate the emergence of entanglements between spin, right? But you in your example, and as far as I understood, you expressed entanglement as the number of even or odd valence bond association. So I like to know if this is the measure of entanglement that is really rigorous, or there is another way to describe entanglement in quantum spin liquid using, I don't know, von Neumann entropy or spin-spin correlation? Is it something more formal that can help to quantify how the system becomes more and more entangled, and what is the difference between short range and long range? Can we have something more formal to describe this?
Yes, so I was trying to give a, let's say, a topological type, so what we call the winding number. So basically a topological index where you can sort of characterize this entangled state. But to measure entanglement, indeed, one uses this von Neumann entropy, and this is also the way you do that in the calculation. For instance, especially when you are doing numerical calculations with wave functions, so DMRG, tensor network, this is the measurement that you use. So this winding number that I was showing to you was in some sense tried to characterize like the Chern number that you know for topological phases. So this is like Chern number, which we call the winding number. So it's just a characterization with a number that whether it has certain, so Chern number, it's 0, you mean you are in a topologically trivial phase. If it's non-zero, your phase is non-trivial. So then you can do some analogy with that.
Okay, wow, that's great. There are, I'm a bit difficult for me to control because there are many questions in the chat. I don't know if you can read some of them. I will pick one more or two. And I want also to ask a question to Luis, because I know that Luis, and you mentioned that mainly all the Floquet physics that is allowing Floquet physics and the discovery of non-equilibrium, let's say, topological phase using light absorption is mainly using light in the mid-infrared. But I was wondering if there could be other non-equilibrium phenomena that could be provoked by using terahertz light, for instance, or even more, if you could combine different type of light source to generate more and different non-equilibrium phenomena that will also conspire or conflict together. Do you have a take on that?
This is a very good question. Actually, at the beginning, the people were thinking more. If you think, for example, in Raman, you think in the visible range, but then you start to realize that if you want to make the effective interaction stronger, you have to go to larger wavelengths, so to smaller frequencies. Mid-infrared turns out to be quite special because there you achieve somehow of optimal range where you can couple strongly with intensities that you can achieve without breaking your material. But terahertz is also very promising. It's also very promising. There are many experiments going on with terahertz, and although the frequencies are smaller and then some effects are not possible, there could be other things that are coming from there. So I would expect also terahertz to be something that we will see more. There have been already some experiments. I remember some by a group in Regensburg, Ganishev, I think they use terahertz to generate some chiral effects in graphene, and this is one way. But there's another way that would be to couple different light sources with very different frequency ranges, and you can think of using one as a source of energy for a given mode in which you are interested in, and using another one to actually modify the material. Then you can play games with this. And with this, I was thinking in one of the last slides I mentioned trying to achieve some intentional design of materials and experiments for non-equilibrium. And so I think that there's a lot of space for this still.
Okay, wow, super. There is a question from Sonia Haddad, I think to Louis. Do you think that the mechanism of superconductivity in twist bilayer graphene is similar to that in cuprate? I'm sure it's a difficult question to answer, Louis, but
well, I don't know, but my intuition is at this point is I would say no. I think if I had to guess, this is not proven, but my best guess at what the pairing mechanism is in the cuprates is in fact associated with spin fluctuation, as in the other superconductors I mentioned. And I doubt this is the case in twisted bilayer graphene, because magnetism plays much less of a role there, it's much less present. So having said that, what is the pairing mechanism? Are phonons involved? These are very good questions, but I suspect they're not the same mechanism, and probably not the same pairing state either. We know, one of the things we do know in cuprates is that the pairing state is a D wave singlet, spin singlet superconductor, and that does not appear to be the case for the twisted bilayer cuprate. Mm-hmm. But that state is not settled yet. It's a very interesting field to follow.
Great. Another question for José, probably from Rocco Martinazzo. Is geometric frustration a necessary condition for a quantum spin liquid?
No, definitely not. What you need is basically a frustration that you have in if you are describing in terms of a spin Hamiltonian. So a mathematical way of describing that is by basically saying that you have non-commuting interacting terms in your Hamiltonian. So I was showing, in fact, the example of this honeycomb lattice, where I was introducing the Taillefer model. The honeycomb lattice is not a geometrically frustrated lattice. However, I was defining a model where the interaction between the spins is frustrated because I'm including different components of the spins which don't commute. So no, geometrical frustration is not necessary.
Okay, wow. So I think there's another question for you, I'm not sure. My question is from Anurag Sharma. My question is, what about the possibility of interaction between spin-on, and in parentheses of a polymer ligand, and a phonon thermal absorber two-dimensional sheet? I'm not sure I understand the question. Do you?
Well, I guess that the question goes into the direction when you start to have interaction of these quasi-particles with other quasi-particles in the system, like the phonons. So of course, in the same way that we talk about the excitations of an ordered system, that these are, so let's say if I have an antiferromagnetic or ferromagnet, the excitations are magnons, and I can have coupling of the magnons with the phonons. I can also describe, if I have a spin liquid, coupling of spinons with phonons. So yes, this type of couplings are possible because the systems have a lot of degrees of freedom, and I may have interactions among these different excitations. I don't know if this was the question, but
yeah, well, I think that's, I might add to that. I think it's a very good question. For example, in the context of the thermal Hall effect that I mentioned, because it's clear that in some material, in some insulators, phonons are carrying that thermal Hall signal. Now, once you recognize that, the next question is, well, how do they become chiral? By what virtue, you know? And most likely it's by virtue of their coupling to their environment. And for sure, if there's an exotic environment with, you know, perhaps spin-ons or other kind of excitations, then that might generate chirality for the phonon. So I think it's a very, very good question in that context.
In fact, now that Louis is mentioning that, we are working with Louis on these questions.
Okay. Wow, exactly. That's unbelievable. We're completely unprepared. So that's really fascinating. That's a strange entanglement.
Yes.
Yeah.
Because we okay. Wow, that's fantastic. I don't know. So there are a couple of other questions, but I'm not sure that maybe they are necessary to answer because they're kind of bit. So yeah, I think it's maybe José, Luis, or Louis, you have a question for the other presenter. So if you do, so you are welcome to intervene.
Well, I have many questions for José, but I ask them all, I ask my questions all the time. So
okay. No, okay. So I think we can stop here. The idea was really to have this one hour and a half session. We had about 100 participants. Now we're 62 still online. So that's really nice. I hope that you have enjoyed this session. I have, as I did, because I'm really excited by what I've been listening, and so I'm sure. I mean, I think I have to invite you, Jose, Luis, and Louis in Barcelona, so that we can continue such kind of discussion. That would be really nice to have you here.
That would be lovely.
Yeah,
Yes.
when the pandemic will allow us to travel more easily. And yeah, so thanks again. We put an end on the webinar. Thanks again to Jose, Luis, and Louis for their kind for the time that they have devoted to the webinar and answering the question. And we have already some pretty exciting debate or new ideas. And I hope you participants have enjoyed, and do not hesitate to contact them. You see, they are very friendly people and very happy to answer questions and to interact with the participants. So once again, thanks everybody. That was a pleasure for me to have this time with you, and I hope to see you sometime in a conference, maybe where quantum materials, quantum computing, all these things will merge together, because it's clearly like a completely emerging field where communities will more and more interact in the future. So bye-bye, stay safe.
Bye.
And
Thank you
very much.
Thanks.
Bye.
Bye-bye.
Bye-bye, have a good evening, have a good day. Ciao, ciao.